Alrighty, so take a look at an interesting example that we haven't seen in a while. Since this week is mostly review, I thought I'd choose a couple of perhaps interesting review ideas. And here's one of them. I want you to imagine if you have a rod, a massive rod or something, like a meter stick or something. So if we have this rod that's kind of fixed in place with a point of access here, and it's just been kind of set up sideways like that, like maybe somebody's got their hand here and they're kind of holding it in place. Now, if they were to suddenly let it go, it shouldn't be a big surprise that this particular rod is going to fall and swing downwards. And the reason it's going to swing downwards is because there's an unbalanced force acting on it. That unbalanced force is the force of gravity that's acting right at the center of mass here. Now, because there's an axis of rotation here, the fact that gravity is acting downwards on it, and the fact that that force is causing a torque, means that the whole bar is going to rotate that direction. Now, the net force on the system isn't zero. I'm sorry, let me say that again. The net force on the system is zero because the pivot provides an upward force at the same time. And this upward force is going to keep the bar from falling to the ground. But there is a unbalanced torque because the weight is acting some distance away from the pivot point, while the upwards force is applied by the pivot point and therefore causes no torque. Now, all of that plays a role in determining what's about to happen, which is the bar is going to rotate downwards and is going to begin to spin with a clockwise rotation. But we could ask the question, how fast is the rod going when it swings downwards by its lowest point? There's going to be this moment in the future where the rod is going to kind of look like this. It'll make it to vertical, and it's going to definitely have some angular velocity at that lowest point as the rod swings past the lowest point. Now, this might not look like it, but this is a conservation of energy question. Although, you might think that energy is not conserved, there is an unbalanced force that's causing the system to accelerate. That unbalanced force is really an unbalanced torque. It's causing the system to rotate, and because that unbalanced torque is caused by gravity, we're going to have energy being conserved. And one of the reasons we can tell is because the center of mass was here, and now the center of mass is here. Any change in height to the center of mass generally points to an exchange of energy. In this case, there is gravitational potential energy here due to the fact that the center of mass is above its lowest point, and if the only force that acts on the system is one that's going to convert potential energy into kinetic, then this energy can be converted to kinetic energy as the rod swings through its lowest point. Now, it's hard to pick out these types of questions and recognize when they're conserving energy and when they're not. So let me just say in the onset that when you have a clear change in height of the center of mass of a system, and that change in height is due to the actions of gravity or the actions of a spring, you are very likely going to be conserving energy and can assume that mechanical energy is being conserved. And we only have three types of mechanical energy: gravitational potential, mgh, elastic potential, 1/2 kx squared, and kinetic, 1/2 mv squared. So in the case of this problem, if we can figure out how much gravitational potential energy there is, we can very likely relate this to the amount of kinetic energy there will be when a rod makes it to its lowest point. So just to put some pieces together here, let's assume the rod has length L. Let's assume it's a uniform rod so that its center of mass is at the middle. And let's assume that it has a moment of inertia equivalent to, it's a rod about its end, so that'd be 1/3 ml squared. And oh yeah, let's not forget that kinetic energy does come in two types, 1/2 I omega squared, and that this rod could have both kinetic rotational and kinetic translational. Now it only has rotational because it's got a fixed axis point, so I don't have to try and decide which kind it has. So let's start here. We're definitely going to have gravitational potential, and since it's mgh, we have to figure out what h is going to be. And in a problem like this, h comes down to where the lowest point is. And the lowest point is based on the lowest point of the center of mass. Well, that's going to be the middle of the rod. So since the rod rotated in such a way that its center of mass started even with the point of rotation and ended directly below the point of rotation, then we can probably say that its change in height was L/2, which means the amount of gravitational potential energy is mg L/2. Now, when it makes to the bottom, it definitely has kinetic energy of 1/2 I omega squared. So if I want to figure out how fast it's going, mg L/2 has to equal 1/2 I. Now I know I can put in that 1/3 ml squared here. There we go. Times omega squared. Now, like in a lot of these problems, we tend to see the mass cancel out. And since we have the moment of inertia in terms of the mass, that cancels out here too. We're also going to get one of the L's to cancel out, but not both of them. So when I work this all together, the left side's going to be, well, g/2. And the right side looks to be L/6 omega squared. So a little more work to do here, and it looks like I'm going to have 3g/L equals omega squared. So take the square root of both sides, and that's how fast my system will be rotating at the bottom. Now there's lots of follow-up questions like how fast is the bottom of the meter stick actually moving when it makes it to the bottom, questions like that. Those are interesting follow-ups, but they're not particularly hard. There are things, though, about that you should be paying attention to, like, for example, the units. G is in meters per second squared. I'm dividing by length, which is meters. So that leaves me with per second squared, and I'm taking the square root of that, which means my units here are just inverse seconds, which is kind of what I would expect for a problem like this. You know, it's supposed to be no units per second for angular speed. So we know that the no unit part means radians. Now we can take this example one step further by, having a disk that's mounted in such a way that it's going to spin about maybe a point near its edge. So you can imagine like nailing a CD into the wall where you put the nail part right there near the edge. It's got the cutout here. Now if you did this, of course, then the whole thing would spin. And this kind of problem is not any different than the rod rotating about its end. It's designed to trip you up because it's throwing at you a problem that feels different than the last problem, but it actually isn't. In fact, for all intents and purposes, it's exactly the same. In this problem, the only difference is that when the disk rotates, it's rotating about this point here on its edge, and now the whole thing is going to kind of be spinning about this point. We're still going to have a change in height that's based on where the center of mass of the disk has moved. So although this problem looks different, and students would see the picture and perhaps have a moment of dissociation or of unclarity, it's still going to be gravitational potential energy here, related to the kinetic energy here. There's a clear change in height of the center of mass. And as long as you can kind of pick out that change in height, and as long as you know that that change in height is due to the action of a conservative force like gravity, then you don't really have to go very far to figure out things like how fast is the system rotating, what is the speed at the lowest point. These are all going to be similar kinds of questions.